Okay, great.
Power. Do we have power coming in here?
Yeah, we do.
Okay, and maybe only 1 minute for a bathroom visit.
Yeah. That's cool. I'm gonna grab some water myself, and then I'll tell everyone to sit down and we're good. Let me see. You go to the bathroom and I'll try to
Where
get the
is
story.
bathroom?
The bathroom is back this direction.
Do you mind if I say a quick announcement about Boston Haskell?
Go for it.
About the Boston Haskell.
Yeah, that'd be good. Actually, it'll make people quiet. I'll tell everyone to get quiet. Let me make this. Let me fix this.
Let me know when I can just leave.
Yeah. Oh, there we go. Yeah, no, that'd be great. That sucks. It's like if this thing moves a centimeter, it does that. I think
is it this cable that's broken? Is it this adapter?
I think it's the weight on this spot right there is my guess.
Because I might have another one of these with me.
I don't know. We need scissors or something to get it off.
Okay.
Let's think about that after this. I'm gonna run. I'm gonna get some water. All right. Okay. Yay! The mic is working much better now. All right, it's time for the talks to start. So everyone, go ahead, take your seats. Ed's going to give a real quick announcement. So I'll go ahead and hand the mic over to him.
Hello. How many people here are actually from the East Coast? Anybody? Okay, a few hands. Maybe this will fall on more deaf ears than I was hoping. Regardless, we're going to do a Boston Haskell Hackathon in August. So Hack Boston, we got some space from the MIT Neuroscience Department. It's a beautiful, huge open space. So I'll be putting up the registration form probably over the next day or two here. And another hackathon on the other side of the continent here.
When is it?
August 1st through 3rd. Hackathons, we'll look for anything, There's also ZuraHack and BayHac, right, coming up. Huh? Yeah, they're popping up everywhere. So, but you should skip all the others and come out to the Boston one. And that's my piece. All right. Daring into a nice introduction.
Yeah, you should have done. But so I hope this is actually recording now on the Hangout. I get we kicked it off, yeah. So it is recording. Do you think? Yeah. Okay. Good. So and I've got to talk to this while looking here. Okay. So well, it was convenient of Gabriel giving his talk because it provides a little bit of motivation for what I'm going to talk about, and some details that I kind of left out of my talk he mentioned. So that's good. That works out really well. So free monads seem to be kind of a popular topic at the moment. There seem to be lots of blog posts about them. But people often ask, well, what does the free mean in free monad? So I want to explain what that means. So that will help you to sort of think about what we really mean by free monad and see the connections to other kinds of things that are free, because there are other things you've almost certainly met that are free that you might not even have realized that they were free things. So, but this is not free as in beer or in speech. So the challenge here is that free is a technical term from algebra, and monads are a technical term from category theory. But I'm going to try and do all of this with a tiny bit of algebra, tiny bit, and no category theory. Okay. So, well, actually, I lied a tiny bit about the category theory because my overall plan for the talk is itself given by a category diagram, but that's okay. It's not the content of the talk. This is just a description of the talk. So I'm going to start with monoids. I'm hoping a lot of you guys know about monoids, and I think I can make that assumption because Gabriel talked about them in his talk. So if you're still here, you must know a little bit about them. Oh, okay, sorry. Okay. And what I'm going to do is kind of take you on the journey from monoids to free monoids. And you may or may not have heard of free monoids before, but I guarantee that if you've written any Haskell code, you have used them. But there's another journey I could take you on, which is a journey from monoids to monads. This is a less well-traveled journey, not that well known. And usually when it's described, it's given in very abstract terms. I'm going to try and give it in more concrete terms, with lots of simple, well, not lots of simple examples, but all my examples will be simple. And then we can combine both of these parts together to get a path to the lower right corner. So this is what category theorists call a push-out, but let's not worry about that. Okay, it's just a diagram showing you the journey you're going to take. Okay, but I'm not quite going to start at monoids because I want to make things really simple. I think each example I give is going to be like the simplest possible thing of that type. And there's something simpler than monoids that's kind of like monoids. Okay, oh shit, wrong slide. So, no, unfortunately, computer science isn't this exciting, right? There's a thing called a magma in algebra, and it's the most boring thing in the whole algebra. Okay, so I had to do the picture to make up for that. So a magma is, well, basically, this is it. The magma is basically, in mathematical terms, it's a set which has a binary operation on it that takes two elements of the set and gives you a third element. That's it. There's nothing more to it than that. But it's an example of an algebraic structure, and it's useful to, as an example, if you want to think about algebraic things generally. So it really is simple. Okay, sometimes you might look at this and you might think, oh, there's some hidden law going on. I mean, monads look really simple, right? There's a couple of lines of code, and there's this gigantic industry of explaining them. But these really are simple. There's nothing more to it than this, really. So simple example is the integers form a magma by addition. Addition is the operation. And there's no other assumptions being made in the magma. There's no laws, no identity, no anything else. Okay? Actually, there's a whole Wikipedia page on these things. It's completely pointless. I think they only exist so that make it convenient to give talks about this kind of thing. So we'll see. So let's say you write a piece of code using a magma. Okay? So this is an accumulate thing. So you have a binary operation that combines two elements together. So you could take a list of elements in a magma and just accumulate them all together by using the binary operation. There's a little problem with that because the empty list has to go to somewhere, so we have to give an initial value to accumulate with. But this is how you accumulate a magma. Okay. So remember, I don't care about magmas. This is just to illustrate some general principles. Okay. So we're not going to use this code for anything. So let's say you wanted to test this code to make sure you've done it correctly. Okay, so a magma is a type class, so you need to pick some specific thing to work with. So you might pick integers. And here's some examples of running it, okay? So this might be a test. You might use Quick Check or some other testing framework for testing this code. And you test it, and 1, 2, and 3 added together give you 6, and 10 minus 10 plus 5 gives you 5, and you think, oh, my code works really well. That's great. So tests are good. Problem is, there's another piece of code. This has a very similar definition. I've just flipped. Go back and forth. I flipped the A and B in the second line. Okay, and that gives exactly the same results on a list of integers. So this test isn't very good. Okay, why did the test fail? Well, for integers, well, I'm going to say times, okay. It's O operation, the operation of the magma. It's conventional in mathematics to call this multiplication, so I'm going to call it times and multiplication, even though it's actually doing addition. It's just standard. So A times B is the same as B times A for integers. No, it's not true in general. It's not. Magmas in general don't have this as part of their definition, but it's true for integers. So this test failed because I did this flip, and this flip does actually work for this particular type. So this kind of leads to the idea of what freeness is. Freeness is basically a free algebraic structure is one that just has the definition as the laws that hold and nothing else. Okay, so what we want, if we want to test this thing, we want to come up with a magma that has no accidental properties. If two things are equal to each other, it's because of the laws that define magma makes them equal. That's what we want. There's no accidents that can happen that could mess your tests up. So, okay, I'm going to switch to some mathematical notation here, but not tricky stuff. But just to say, well, just for the hell of it. So we want to find kind of the least special magma, the one that has no special laws. So suppose we've got two elements in it, A and B, and let's suppose they're not equal to each other. Okay, so what else do we know about this magma? Well, we know that the product of two elements must also be in it. Just by definition, there's a product operation. And again, I'm using normal multiplication, writing A next to B to mean multiplication. Okay, it's shorthand. And if we don't have any accidental equalities going on between elements, we know that AB can't be the same as A, and AB can't be the same as B. And similarly, we know that A times AB must also be in this magma. And it can't be equal to any of the other things either. So you can see how this just goes on forever. There are more and more of these elements we could keep throwing in, and we want them to all be distinct from each other. So we need to come up with some data structure that represents them. It's going to be called the free magma. So, okay, so let's just think about a typical element of this thing, like A times B. We can represent that as a tree. So I've got the O as the branches. I don't know what you call the internal node. Well, the internal nodes, and A and B are the leaves. Okay, the variables live at the leaves. Okay, so an element of this magma with no extra laws looks like a tree. So it's pretty straightforward. We can just define a type to represent this thing. It's just a tree. So an element of this thing is either var A, where var just means variable, and A is the name of the variable. I'm allowing any type. It doesn't just have to be a string or a letter, any type. Or it forks into two subtrees, and that's it. And this is, in fact, a magma. So this thing is guaranteed not to have any accidental equalities in it, because every expression that you could write is distinct from every other. They're all completely different expressions. Okay? So if you were writing code to test magmas, this would be a good thing to use. I'm not really talking about testing, but it's good to get the concept. Okay? There are no accidental equalities with this thing. So, but that's one way of approaching.
I'm sorry to interrupt, but could you speak up a little more?
Oh, sorry. It's tricky, because if I get closer, I'll probably whack this thing. Yeah. Okay. So, now where was I up to? Oh, by the way, if you want to ask questions, ask at any time. And if that goes wrong, then I'll ban questions from that point onwards. But, but for now, it's okay. So that's one.
Why do you have var A with A being a type variable? That's opposed to having some specific name?
Well, it lets you choose whatever type you want to represent your variable names, that's all. It could be string or something like that to represent names, but it's a more general purpose, useful thing. I mean, it's a tree. Trees are useful. You can store whatever you like on a tree. Right?
Would it also be free if it was just unit?
So if it was just...
Yeah, would it also be a free magma instead of a unit?
Oh, yes. Yeah. What I should say is it's not, no such thing as just the free magma. I've got to say this. There is the free magma generated by something. Okay, so A is the generating set. So you're starting with just elements of A, and then you can build the entire type from that. Sorry, I forgot to say that. So yeah, you could use whatever you like as A. So that's kind of an informal approach to what freeness means. But there's a very important property of freeness that's in some sense the essence of freeness, which is the way mathematicians look at it. But I'm still not going to get too embroiled in mathematics. So here's the idea. So I said that elements of this free magma are basically expressions that you can build using the language of magmas. It's a very impoverished language. It just has binary operations. Okay. So you have variables combined together by multiplication, but you want to be able to substitute actual values for those variables at some point, and then evaluate the whole expression. Okay, so this is the crucial operation, right? You have this magma thing. Well, you have your element of the free magma, right? Well, in fact, let's go back to the types. The underlying type A, okay, which is the labels of the variables. We want to assign to each of those things a value in another magma somewhere else. So we're actually assigning a value in. And then we expect there to be a function that can then evaluate the entire expression based on that assignment. I'm going to give a simple example of what that looks like. Well, this is what the implementation looks like. It's pretty straightforward. If f is a rule telling you how a variable name maps to a value, then you can just apply f to whatever's in the variable constructor. Otherwise, you just interpret down the tree and then combine the results together using the magma operation. Okay. Well, that's what I just said, so let's skip that. So here's a really simple example of doing that. Okay. So I've made one of these trees, which corresponds to the expression I had earlier. I've written a function that maps A to 1 and B to 2. So we're working with integer here, so we know that AB is 1 plus 1 plus 2, so the result should be 4. And then we can interpret using f our expression. Okay. So what's going on here is that we've kind of separated, in a very simple way, syntax from semantics. We could compute expressions in this magma thing, but actually what we do is we build expressions in one phase, and then we evaluate them afterwards by substituting the variables in. Before we actually have values for the variables, we can't really evaluate it. But it's curious that the actual expressions themselves, the bare expressions, they actually form a magma as well, which is kind of interesting. But this is what freeness is all about. This is what free means. Yeah. And you can generalize this to other things. So now we can get to monoids, okay? So monoids, forget everything about magmas, basically. You don't need to know about them ever again. So monoid, it's kind of a bit like a magma. You have this binary operation that combines two elements to give you a third one. And there's also the empty element, okay, or the identity element. And a well-known example is integer. And so the only change from before is that now we say that the identity element is 0. And the catch with monoids is there's some laws you have to satisfy. Just implementing this interface isn't good enough. So I'm hoping people, I mean, this isn't meant to be an introduction to monoids, so I'm hoping you're a little bit familiar with these. But so the idea is that if we multiply on the right and then multiply on the left, we should get the same results multiplying on the left and then multiplying on the right. And I'll give a little bit of motivation for that in a bit. And then the other laws are these. So, okay, so can we go ahead and make a free monoid now? It seems like it's going to be straightforward. We just do the same thing as we did with magmas. Free monoid A, so we have a variable. We know we can combine these things. Well, we know there's an identity element. And we know we can combine pairs of free monoid elements to make a new element. So this looks like it will do the job. And in fact, it's an instance of monoid, which is cool as well. So it looks like we're well on our way to a solution. But it doesn't work. It doesn't satisfy the monoid laws. Okay? Because if you multiply your identity element by any element, you should get the element again. But you don't. You get a bigger structure. You get a tree, an expression that represents that. So we need to find a way to make this happen. We need to make these things equal. So if we look at the laws kind of pictorially, right, we have A times BC equals AB times C. And that basically says that if you have the tree on the left, you can convert it into the tree on the right, and they should be equal. But that's not true for the trees that I just defined. So that's why it doesn't work. These are distinct trees. So we need to find a data structure where you can't do this kind of shuffling. You need to find a canonical form for the trees, basically. So, for example, if you have an expression like this, where all the multiplications are kind of nested on the left, we can just use the monoid laws to convert that to expressions nested on the right. And put an identity. I'm using E for identity. Mathematicians often use E to represent the identity. So I'll put an E on the end. It's unfortunate that it's the letter after D, but it's how it is. Looks like part of the sequence, but it's not really. So pictorially, that means that in principle, any of those trees should be equal to one that looks like this. You have a spine of I can't remember what I called it. Tree. Yeah, it should be tree actually, not diamond. Okay, with an E at the end. And that should be kind of familiar. That should look like some data type that's well known. In fact, I replace the names of the constructors. They're basically lists. So actually, if you want, the free monoid is the list. So this is, in fact, so list in fact form a monoid. So this is actually the free monoid. Okay. So if you think about it, a list is basically, it's just a list of elements. And that's what expressions are in the language of monoids. They're just lists of elements that you're going to multiply together at some point. Okay?
How did it become star and E instead of?
You know what? That's my mistake. Yeah, I went through and tried to fix. I changed the name of everything at some point, and yeah, that's a mistake. That's a mistake. Sorry, I missed that one. Okay, well that's fine. I haven't reached my threshold yet. So I mean, one application of that is if you want to test monoid functions, lists are a good thing to use for testing. Okay, so we can mimic the whole interpret thing again as well. Okay, so we expect to have a function that you give an assignment to the variables. So each variable will be assigned an element in some monoid, and then this interpret function will then allow you to provide a list and evaluate the whole thing. So I don't know, do you guys recognize this function from somewhere? Because it's a pretty well-known kind of function. Well, it's actually map reduce. So what's happening is that you're using F to map all of the elements to or fold map as well. Yeah, officially called fold map. Yeah. But conceptually, it's map reduce. Yeah, you're mapping each element to some monoid, and then you can use the rule in the monoid to combine them all together. Okay. So it's the interpret thing that's the really key thing. But it's just variable substitution, basically. So it's a different way of looking at map reduce type operations. So, okay, so I'm going to give a really stupid example, but simple examples help, right? So again, this is whole syntax semantics thing going on here. So we'll make up some syntax, right? Some bank operations with a bank account. So you can deposit an integer amount of money, or you can withdraw an integer amount of money, and that's it. And then we can arrange an, I've just got withdraw wrong as well, but never mind. So we can write programs using the language of monoids, which is basically just stringing things together in a row. And that program doesn't do anything. It's just bare syntax waiting to be evaluated. And then all I have to do is write a piece of code that gives an interpretation to one of those things. Okay, so in this case, interpretation is going to mean how much has the bank account changed by doing these operations. So I just have to give the rule for each of the objects in the list, and then the interpret monoid function stitches them all together and tells you what a whole sequence of operations do. Okay. So again, this isn't necessarily something you do in the real world. This is just to get in your heads the concept of separating syntax and semantics. In fact, we could provide completely different semantics for this. We could actually, for example, print bank statements out or whatever you want. So, just want to go back to the associativity thing, just to motivate that. So, the idea of associativity is that you can multiply on the left before multiplying on the right, or do the other way around. And so here's an example. We multiply 4, 6, 2, and 3 together. You could work on the left, or you could work followed by doing the right and then combining the results, or you could choose a completely different order. So that's a crucial thing about associativity. It just allows you to change the order in which you do things. You're not changing the order of the operations, you're just changing the order in which you reduce these operations down. Associativity is really useful for humans, actually, because it allows you to reason about things. If you've got A times B times C, you can chunk the A and B together and not worry about the C, and reasonably reason about it reliably. The C doesn't affect the A and the B in some sense. And we'll see a picture like this coming up with monads as well, so it's worth bearing that in mind. The problem with monoids is that they're very limited in what they, there's a syntax for computer programs. It's just a linear string of operations, and computer programs are more complex than that. So it's good for a very limited kind of operation, but not for general purposes. Okay, so for example, what if we want to have computer programs where one of the steps in the chain actually forks and chooses one direction or another depending on some kind of input or something like that? It doesn't make sense. Well, you can kind of do that with monoids, but it's ugly. So instead of this, we want this. So we want a branching tree structure instead of a linear list. So how can we do that? So how do we design such a thing? Well, so in monoids, you multiply an A by a B. Okay, so the multiplication operation has one thing on the left and one thing on the right. But we want to see kind of a tree structure emerge. So we want to sort of tweak multiplication. So maybe you have one thing on the left, but you might have a bunch of things on the right. And the bunch of things gives you basically the collection of different branches you could take. So, okay. It's kind of tricky because you might want to have different branching at different points in your representation of your program. So, okay, I could mention some ways of doing this that are non-starters, like, well, not non-starters, but that aren't as elegant. So, for example, you could associate with every element in your algebraic structure, whatever it is, an integer that says how many arguments it could take on the right. Okay, so you could have some that take 2 arguments, some that take 3 arguments. Okay, but we could try and generalize all the way. What we could do is, this is slightly weird, but we could say that each element in our algebraic structure is itself a container that contains the things that are going to be on the right-hand side of the multiplication. Okay, so as a special case, you could imagine containers that contain only one object, and that would give you back monoids. Okay, so the way you'd multiply things in this kind of structure is that you take all the things on the right and the thing on the left, and you'd stuff all these things into the thing on the left because it's a container, and then you'd apply some kind of unary operation to smush it all down. But it's very similar to doing monoids. It's just convenient to stuff things into a container first before doing an operation, and that means that you can use any container you like, and you're not just limited to things that contain one object. So this is a nice generalization of monoids. So again, how do you design such a thing? Well, we'd like an identity element in there. And the identity, we want it to be a bit like the identity in monoids. So it needs to take some argument on the right, one argument, let's say, on the right. So the identity itself needs to be a container that you can stuff one element in. So this is kind of what it's going to look like, this monoidy thing. It's going to have an identity which basically takes an object and then makes a container with one element. And there's a multiply operation. So what's that going to do? Well, you're going to have a bunch of things in a container, or a bunch of containers of things, and you're going to make a container of those containers, and you're going to smush it down one level. And that's basically this is basically the code for what I just described. So you recognize that? So if I rename things, it should become more familiar. That's what a monad is. Okay. So a monad is basically just like a monoid, where you can have an arbitrary number of things on the right-hand side of the multiplication. So you might not recognize it because I've called something join. Join is just a slightly different definition. You can get back to the usual definition by doing this. Okay. In some ways, I prefer this as a definition of monads. Okay, so for example, the monad laws. So what we're saying, so if you go and look online, you can see some of the typical laws for monads using the join operation. One of them says that join.join is equal to join.fmapjoin. And pictorially, that's just saying we could do the smooshing on the left, or we could do this smooshing on the right first, and we get the same thing either way. So the reason why there's an fmap join here is that to do the smooshing down on the right, we need to do it on all the things inside the container. And fmap is the thing that lets you push a function down to all the things inside the container. Okay, so this is just an analog. The reason why I showed you the monoid diagram before, showing you the different orders, this is almost the same diagram, except we have trees now instead of linear lists. The monads are really just kind of monoids in disguise in some ways, generalized. So now you may be able to guess what a free monad is going to look like. Okay, so instead of lists, these things are going to be trees. That's basically what a free monad is. It's just a tree. Not much more to it than that. Okay, so they're going to be built from some base elements. Okay, just like with lists. Okay, but one thing that's different here is that the base elements, as I mentioned, you want these things to be containers, so there's a space to stuff in the things on the right-hand side. So we actually use containers instead of normal elements. Okay. So Gabriel actually did something similar to what I'm going to say here. So let's think about lists again, free monoids. You can sort of write it algebraically like this. A list is either the type with one element or a pair consisting of an element and a list. Okay? So algebraically like that. In Haskell notation, it just looks like this. Standard definition of a list. We can kind of try and mimic that. We sort of want a solution to this equation. One of our trees is basically either the identity, which basically contains one of these base elements, or it's a container of the free monad. And this is what the definition looks like. Completely mimicking lists. So join is basically the multiplication operation. This is what it looks like. We don't need to worry too much about the details of it. I just want to show it for completeness. But using this join, we end up with it. This actually is a bona fide monad. It satisfies all the monad laws. And I'll have some pictures later to show what these things really look like. So then we have this, we want to interpret these things. So there's a corresponding interpret monad to go with it. Again, I don't want to get too bogged down in the details. Oh, it's also a functor. That's pretty straightforward. It's very easy to make trees into functors. Functor being almost synonymous to container. So if we look at the type signature for interpret monad, it's a little bit tricky, but it's the same kind of thing. So before, we were assigning values to elements, and that allowed us to evaluate the entire expression. This is going to allow us to assign trees, but it's slightly weird because we have the for all, which basically says the function is polymorphic. So we expect it to pass a fully polymorphic function into this function. So you need a Haskell extension for that. But the idea is that A, in the interpret monad type signature, A is just any old functor, B is another monad, and we're basically saying how to translate our basic generator containers into monads. And once you've done that, interpret monad function can convert that to interpret an entire tree. So this is the key thing, just that type signature. And I'll give some examples. The examples are really simple, and the examples are much easier than this type signature, so it's best to learn by example. Okay, so here's an example. It's like the simplest example I could think of. So let's make up a functor. So a really simple functor is like a pair operation that basically has two things in it. And it's a functor because we can implement fmap. So we just apply the function f to each of the elements. Okay, so we should be able to build a monad from this. So this will be, the free monad from this is just going to be binary trees. So you either have leaves, which are the things I've been calling variables, or it just splits into two with subtrees. So that's what you're going to get. Okay. So we're going to want to build these things up. So it's nice to start with an actual instance of this thing. So here's a convenient one that I made. So it's a container with two things. One's true and one's false, and that's it. Okay. So what can we do with this thing? Well, firstly, you might not want to have yes and no in the leaves of your tree. You might want to stuff other values in there. In fact, if you want to build up big trees of these things, you might want to stuff trees in these things. So you need some way of stuffing values into the leaves so you can grow your trees. Well, we can use fmap for that. Because I store true in one half of choice and false in the other. So we can just use an fmap to put any value we like in each of the two halves by just doing an if statement. Okay? Well, we can rewrite that code a little bit. And by the way, it always does, it just build a tree, okay, with our chosen values in the leaves. So we can rewrite that code a little bit. This is equivalent code, using standard properties of monads and fmap and all that. Now it's beginning to look kind of familiar. It looks like x is somehow assigned a value that comes from a choice somewhere, and then we're returning something that depends on that choice. But this code doesn't do anything. It just builds a tree. But it looks like it does something, which is cool. Because now we have some kind of language here that we've extended with some kind of choice operation. So how do we, what kind of code could we write with this? So here's in fact, this is very similar to an example that Gabriel just gave, actually. So we can use this just like monads you're familiar with. A gets one of these choice things, whatever that means, and I haven't said what it means yet because we haven't assigned a meaning. B does the same thing. And then basically this code does nothing but build this tree. And Haskell being lazy, of course, it doesn't really build the tree. It promises to build the tree, and whatever part of the tree you explore, that's what it actually builds. Okay? So this is kind of readable code, but it doesn't do anything yet except build a tree. So we'd like it to do something. So this is a cool thing. We've got a representation here that doesn't do anything, but we can do what we like with. So we've separated this kind of choice functionality from the actual meaning of choice. So here's an example. There's somebody typing in true, false in. So remember I mentioned with this interp monad thing, we need a way of translating our functor containers to a monad container, and then it can extend it to the entire tree. So here's an example. I'm telling it how to interpret the choice thing in the I/O monad. So all it does is read a value from the terminal, and then makes a choice based on it. So I've just had to say how to do the choice thing, and everything else just follows. So now if I interpret this, this piece of code, because I've applied it to test, this is test. This will now receive two inputs from the user, and then print out whether or not they were both true. But this wouldn't be useful if to refer to a previous question. I mean, there's no point separating the syntax and semantics if you're just going to evaluate the semantics, apply some semantics to the syntax straight away. But you can do other things. Okay, we can try a different monad. We could use reader. So now every time you use choice, it's just going to return the value in the reader monad. So in this case, I'm testing it with true. Completely different semantics for the same piece of code. So this gives a lot of flexibility. And here's another example. This is reading an infinite stream of, well, it could be a finite stream of truths and falses using the state monad. And again, the pattern here is that we're mapping from our functor to a monad. So we have this it has a great way of completely separating the syntax and semantics. And with lots of advantages that brings. I mean, one, conceptual clarity. It allows you to separate these things in your mind, just implement one, and then implement the other completely separately. There's all kinds of other interesting things you can do, like actually coroutines is a good example, and this will help motivate maybe Gabriel's definitions. I'm not sure though, because I haven't looked at the internals. But let's say you wanted to implement coroutines. You might want to have different trees executing alternately, or with some kind of scheduling, which means that you have to kind of freeze one computation and then do another one, and then freeze that and come back to the first one. Well, if the computations are themselves just trees, it's really easy to reason about. If you don't do that, you might find yourself messing with continuations and getting very confused. So these are very easy. You can also, to some extent, inspect them because they're trees, which is useful for debugging. It's not totally true. As soon as you start playing with these things, you'll discover that promise might melt away. But to some extent, it is true. And certainly, if somebody just gives you a tree, you can do case analysis on the root to see what's going on. So it's very helpful for debugging. And so I usually, oh, yeah, you have a question?
Should there be a cycle there for the initial state?
The cycle?
Because right now you can run out. You're still getting it.
Oh, yeah, yeah. Oh, hang on.
You only eval with 2.
Yeah. Right, okay, yeah. So, yeah, this case doesn't matter, but yeah, in principle, I should, well, I'd rather use a stream type than a list type. So, but, yeah. So this code's written in a very specific way. It's converting from a functor to a monad. But you can actually write the whole interpreter yourself. You don't have to use this insert monad thing. And then you don't have to worry about the for alls. So I could rewrite the code like this. So this is kind of similar to the kind of code that I've seen in various tutorials. So now the interpretation of the ID, the variable thing, now doesn't come for free, so you have to implement it. But this is just a tree, okay? It's just an abstract syntax tree. You can write any code you like to interpret these things. What's cool is that you get the monad notation to build the tree, which is very, very elegant and readable, and then you can write any interpreter. Yeah, yeah. So, in fact, the way I've written this code is I've still fitted it into the same style, where I'm mapping to a monad on the right. It doesn't have to be a monad. I mean, it's just a tree. You can just interpret it however you like. Okay. So this is actually pretty well the end. There's lots of stuff that I could say, but that stuff is all already out there in blogs and tutorials. I've tried to give a different perspective on where free monads are coming from. And I'm hoping this will help you think about, reason about stuff that you read elsewhere. So there's tons of polls, tons of stuff I've left out. So perhaps some suggestions of places to read. I'm certainly going to put this stuff online. Gabriel's article is great on free monads. If you want a sort of more theoretical treatment that's still not too crazy and out there, Dan Dole did one, which I thought wasn't bad. So go off and read some tutorials now, and I hope I've given you a deeper understanding of what's going on. I've not actually seen anyone present monads in this way before. I found that quite useful to think about them, so I'm hoping, if nothing else helps, that might help some people. Okay, thanks. So,
Do you have questions now?
yep.
Granted that the FFP is
Yes, I'm being asked why it might not be so useful for debugging. So the reason why is that quite often the functor you use, so I gave an example where it was just a pair of elements, okay? So we could rewrite that slightly differently. We could make that a function that's a bool to something. But as soon as you use a function, you can't just inspect it anymore. You have to actually execute the function. And in practice, that's how they are. So in practice, these things are actually continuations that are in there. But I don't want to talk about that too much because you can read other tutorials on that. But that's the problem. You pretty well have to execute the thing before you can get the things to unpack. So, but it's quite easy to insert debugging code into the interpreter and things like that. So, yeah.
So in your monad example, you showed so how your original free monad is going to violate the associativity law.
Yes.
And doesn't the free monad there sort of violate the associativity law in a different way?
Actually, I should think about this, but I think So
The borrows the associated.
yeah, exactly. Functors are associative automatically. So if you make a list of a maybe of a list, it doesn't matter which way you group that. It's just the nature of the language that it comes for free. So yeah, actually, I got worried about that at one point. Oh no, this is going to ruin my whole talk. But no, it works.
But in one sense, if you nest all your replies on the left, it's going to be different from nesting all your replies on the right. Because if you want to substitute in, that's the left nesting.
Yes, another performance.
Yes, performance is different.
Yeah, yes, that's true. Yes, and so kind of curious thing here is that so you know the trick with yeah. So basically, you know, if you go back earlier than that, you know the Hughes list trick. Okay, so now the codensity trick kind of becomes easier to think about when you see the analogy between monads and monoids and monads, because it's basically the same trick. It's exactly the same trick.
Wait, what was that?
Well, I can't remember the name of the paper.
The one for
Asymptotically improving.
doing the difference lists.
Yes.
Basically.
Yeah.
Doing composition of.
Oh,
But it works for monads as well. And the sort of analogy between monoids and monads here should make it clearer why that should work. So you might almost have guessed that technique was possible based on this analogy. So,
Okay.
okay.
The smaller.
the follow-up to that is, if you have, if you're using sort of the free structure, so you're basically implementing a return and a join. Right? That's your structure.
Yes.
And then you're getting the map functor.
Yes. Hang on.
Well, I guess my question is, can you build the same structure using a find constructor?
Oh, that's a good question. I actually haven't thought about that.
That's the operational monad that is used by.
Yeah.
Right. But then would you then I think you would not have to use a functor.
I'd have to think about that.
That turns out to actually be another, like, let's play games with the data and codensity. That turns out to be the free monad of the co-unit data of F instead of F.
I'm stepping in as organizer to see if there's another question, because no one can hear you guys.
Okay,
sorry.
Another question somewhere else. So on your slide about sort of what the essence of freeness was, did I interpret you right? The idea is use the data structure for polynomials exactly the next to the other one.
So I didn't hear that one.
Sorry. Because the idea was sort of the kind of essence of what freeness is. You end up with a data structure, polynomials match.
Yes. Yeah. So the question is, well, actually, that's part of the definition of You're trying to come up with a data structure so that the laws associated with your structure are already built into the data structure. So you can't possibly accidentally have two things that are not equal to each other that you want to be equal. You're just finding a canonical form. So in principle, you could take any type class and try to make a free version of it, or at least a certain limited set of type classes. And quite often, it's very hard to find a type that's appropriate. But the question of when something's equal is kind of a subtle question as well, because what you could do is, okay, their data structures might not be equal, but what you could do is hide that behind an interface. And then the interface doesn't allow you to see that these things are different. So as long as you use that interface, you're fine. So that's another approach as well. Yeah, see, so because we don't have sets, for example, yeah. But there may be, I don't know, on a case-by-case basis, there may be ways of doing it, but I can't say generally. Yeah.
There's a nice, cute little.
Oh, okay, yeah, tell me afterwards. Okay.
Is there a similarly nice integration for free monads? Can you say something like
So, what I'll say is that okay, so the question was, is there something similar I could say about code-free comonads? So code-free comonads. So I was expecting that question. Just as things, as opposed to co-things, things are trees, but monads are kind of trees of some sort. Co-things are kind of state machines. So that's really what's going on in the code. There's different ways of looking at it, but that's one way of looking at it. They're state machines. And a code-free comonad is kind of, well, just as the free monad, we take some representation, this tree representation, and then we kind of expand it out with an interpreter into something that does something. we sort of do the other way around. We kind of package the big, complicated thing into a machine with some kind of state machine with transitions. I'm trying to think if there's a better way of saying that, but that's really what it is. So when Gabriel says, he wrote a blog post talking about how comonads are kind of like objects, because what happens is especially if you have an object in a programming language like C++ with mutable objects, you can call the methods on the object, and those methods update the internal state. So this kind of like thing where you have a whole bunch of different methods that you can call to update the internal state. That's what code things tend to be like. So, or at least some of them. He's shaking his head, but
Different intuitions.
yeah. And these are related because if you try and map out a finite state machine, you end up with trees, which is what monads are. So there's some interrelation between these things.
Monads let you redecorate. Trees let you substitute.
Yeah.
Monads let you substitute.
Okay. Any other questions?
Okay.
Okay. So maybe I should stop the.
So we have like 15 more minutes, so we can just sort of hang out, and then we have to. Before everyone leaves, make sure that you look at the list back.